Okay, thank you very much for coming back. Maybe it's the feeling that the room is smaller. Okay, so we left this morning with this beautiful picture where the labels, the axes, were labeled by these arcs. And these things, I remind you, are really non-perturbative objects. So this plot is really exact. And so the question now is, what do we learn in terms of physics? From these infrared UV relations. Okay, so there was this beautiful mathematical structure behind it, but now we kind of come back to the physics and understand how this tool can be used to answer the question that I laid out this morning, which was understanding the structure of these couplings that we have in this Lagrangian and see what hierarchies they can take. And so I will start to approach this question in I will approach it in a perturbative way. So first, I will use this Lagrangian to compute the amplitude in the effective field theory at tree level and compare it to the bound. Again, the bounds are non-perturbative, but what is perturbative is now the derivation from this Lagrangian to the amplitude for 2 to 2. And this is already prepackaged with the right coefficients such that the amplitude takes this form, and so on. So there. Okay, blah, blah, blah. So from this Lagrangian, you compute it at tree level, and that's what you get. This is where perturbation theory comes in. And so the first thing Now what we do is that we insert this in our infrared UV relation, that these arcs in the infrared, they can be computed by residue theorem. I remind you that in our plot there were the integrals along this half arc of the amplitude divided by certain powers of s. So, in fact, when you compute this thing, the arcs are in one-in-one correspondence with this coefficient here. And in particular, the one with this, sorry, let me rewrite the expression of the arcs, which is an integral over the amplitude divided by 2n plus 3. Okay, so the zeroth arc is G2. There might be some factors too that I'm neglecting anyway. The first arc is G4, and the second arc is another guy G6, which I've not written there, and so on. And in particular, what you see is that the first coefficient, the lambda in lambda phi to the 4, is invisible to this story that I've been telling. It doesn't enter in these arcs. And this is a fruit of this twice subtracted dispersion relations, that basically this constant doesn't have, doesn't leave any trace there. And the other thing that you also see is that couplings that contribute in the amplitude with this type of terms, S2, they vanish because we're working in the forward limit, okay? And of course, you know this crossing symmetry implies that the only two structures that can enter in your amplitude are S squared plus T squared plus U squared, or STU at tree level, okay? Good, so now is not, we can reinterpret these bounds in terms of these couplings, and the first thing that we see is that the fact that we are within here and within here implies that all these couplings, besides being positive, they are also monotonically decreasing in units of the energy. So, okay. So they're organized in a strictly decreasing way in units of the energy, which is an energy within the effective field theory. Because that's where I can use these answers, okay? So if I try to, if I compute an observable using this theory, I can plot how the amplitude goes as a function of the energy, and well, the piece G0 is just a constant here. An amplitude that increases like S square. This is, for instance, the amplitude for pi zero scattering. And the question here is, can we have an amplitude that increases faster than S square? And from this relation, we see that the moment that a term with more powers of S beats the S squared term, you're violating this relation, and basically your theory cannot work here. In other words, you have identified the cutoff of your effective field theory as the value in which any of the higher derivative couplings takes over the leading one, G2. So this is the maximum energy that is allowed within the effective field theory if you want to have a unitary UV completion. And this is...
is it similar to Froissart?
To Froissart?
Yeah.
It's a consequence of Froissart. No, sorry, it's not. I see what you mean. No, it's not similar to Froissart because it derives from Froissart at high energy, but this is within your effective field theory, right? You can indeed. This one violates Froissart by zero scattering already in that sense. You cannot have it asymptotically. Yeah. Right. So what we learn here is that the symmetries that we had before, that were spelled out before, like the shift symmetry associated with the pi zero is a good approximate symmetry in your effective field theory, and instead other symmetries like that had this more complicated structure, these are not allowed within the effective field theory because they're not allowed to be approximate symmetries. They are always broken by order one effect, meaning that this S squared term is always there, and therefore you never enter a regime when you see this. Or differently, an experimentalist measuring this will never see a behavior that has more powers of S. And for those of you who liked the Munzat's theorem this morning, this result tells us that basically this idea that higher derivative terms could pick up the role of lower derivative ones does not work, because having a lower derivative coupling like this one to zero would violate this bound and therefore is inconsistent. Okay.
But if you are talking about pi scatter, then there are some threshold, right? Chimeson, nuclear, whatever. They will change behavior, right?
They will change. Yeah, but that's the point. These things will happen here, right? Your raw meson and all the guys. My statement is, what is the maximum cutoff allowed within your effective field theory before you?
So it is below raw meson?
Yeah, below the raw meson.
Nice.
Yeah.
This is on equal at 11, right?
Exactly. I'll come to this in a second. Right, maybe a quick comment on back to this picture, it's interesting to ask what are the theories that live at the boundary, that saturate these bounds. And in fact, there's a nice story that relates in part to some of these theorems that I mentioned, and in part to thinking about particle physics, which is the following. So here it is. These semi-definite conditions that I mentioned before turn out to be saturated in theories that have a zero measure in the UV. So theories that are made only of delta functions, or else theories that are weakly coupled. So at the boundary, we necessarily have theories that are weakly coupled also in the UV, not only in the IR where the effective field theory is valid, but also in the UV. And indeed, you can look at this thing, and what you find is that the boundary of the two-dimensional figure is captured by UV theory with one particle. Instead, if we look at the one with the more dimensional one that I'm not able to draw, the boundary now is spanned by theories that have two particles in the UV, and so on. So there's this nice characterization. In fact, along this curve here, you just have a scalar of a mass m, and as you take the mass of the scalar larger and larger with respect to your energy, you move along these curves. Okay. Yes?
So you mean that when you say delta functions, you mean that it's saturated by a model where you just have tree diagrams?
Yeah.
So it's something like a large, but it's one particle.
One particle on the two-dimensional, on this plot. The three-dimensional plot, where I also include the next guy.
But okay. I'm not worried about more parameters. I'm just confused because that theory is not unitary.
Exactly. Very good. Indeed, this is the limit of.
We haven't imposed full unitarity, so maybe that's just the answer, right? But
it's partially the answer, but it's more has to do like semi-definite. We impose the semi-definite condition. Indeed, imposing positivity implies that the boundary is not there, that we're always within the boundary. So it's open.
Sorry,
set.
what does it mean? Why is it unitary? Just to have one?
No, because they're very having yeah.
that's all.
Okay.
Okay. So I was just asked about that this is a tree level. In fact, indeed, this implication here is a purely three-level thing. So what happens instead? If you compute at the next order in perturbation theory. First of all, this is a necessary thing because we are doing all this talking about unitarity and analyticity, and then what we do, pang, you put in an ansatz which is not unitary because this is as non-zero to scattering, but imaginary part is zero, right? So yeah, you're already violating your input hypothesis with the ansatz you choose. Say differently, in terms of the analytic structure that we have been looking at, so far we had a situation which was like this, but the non-analyticities were only associated with the UV, but instead, the more realistic one is this, where you also have something in the infrared. So this is 3. And now we want to look into this. So the first qualitative features that appear beyond tree level, I mean, it's one loop, but I would say that that's all that it's interesting to look at, right? We go on one loop, now we get a realistic structure, and we see what qualitative consequences of this argument change, and then presumably at higher loops, nothing qualitative will change. But here something actually is different. So now my amplitude, we'll have the 3-level pieces as usual. But it will be other sorry, I'm looking at the amplitude. So from this diagram, we'll have contributions that have this logarithmic behavior, and here beta 4 comes from loops involving the coefficient g2. So this is something like g2 squared divided by 160 pi squared, I think. 7. Okay? And then this continues with terms at higher order. There's a beautiful piece like this that comes from log s minus log of minus s. And then we have s to the 6, g6 plus, again, some beta. Okay, so good. The appearances that we have here is this term here, these terms here, and this term here, which are non-analytic in the infrared. Okay, so this we can call this whole thing G4 of S, the running G4 coupling, and this one is the running G6 coupling. So you might think that all that happens here is that I just replace all my bounds, all my comments with running couplings. But this is not all there is. In fact, there is something else that happens because when you look at arcs, now these pieces enter in a way which is not just associated with the running. And in particular, let me show you what we get. We get a okay, sorry. I've highlighted in red the parts that we should pay attention to and that are genuinely new. So, as I say, the first arc now will include the running coupling, which is not very surprising, but the next guy will have these pieces which are polynomial in 1 over the cutoff. Okay? So these things are, they don't just behave like logarithms that we can easily understand. These are things that eventually dominate over statements on their running couplings, okay? And they dominate polynomial. When you go to low energies, these things become bigger and bigger, and finally your statements on the actual Wilson coefficients kind of become fluffy and you don't see them anymore. You can understand why this is the case, because, as you know, running induced by the more relevant operators always dominate over very relevant couplings. This is, I guess all of you are familiar with this in some context or the other, but it's basically the idea that a super irrelevant guy like G6 or G100, how can you distinguish it from a logarithm of something more relevant, okay? And but what does it tell us? Well, it tells us that, for instance, now this coupling G6 can be smaller than 0. It's no longer strictly positive. The coupling itself can be smaller. Remember, this is a statement that the arc is still non-perturbative object and is positive, but when you translate this into your Lagrangian couplings, there is this kind of glass that distorts things, and the couplings now have this behavior. You can have these negative things there. And yeah.
I don't know if this is a question or comment, but I wanted to maybe slow you down just a little bit here, maybe so I can catch up.
Sure.
So I guess somehow there's something that looks a little miraculous here, because if you're just an ordinary EFT guy, you always expect to see slop from higher dimension operators. Okay, but actually, way back before you even started looking at trees, you see that that's not the case, right? So like A0 and A1, at tree level, there's no slop whatsoever from higher dimension operators, right? And somehow that's kind of the miracle here. We know that there has to be, somehow EFT breakdown has to show up when you take S too large, but it shows up, it doesn't expand the system into an infinite number of unknown constants.
No, it's here. It's
somehow this is.
No, it is here, Marcus. I haven't written. It's in the dots. Let me come down to the here.
Maybe it is a question.
Then it's a question. Yeah. Let's indeed here. If I understand correctly, you're pointing out there will be, for instance, the B6. Well, it was here. Sorry, I erased it. And B6 is when you have like G3 and G3, for instance. Inside, we can have a contribution from G6, G8. All the couplings will contribute to this loop, and somehow they will all appear here. You'll have all the.
Oh, okay. So they do come back down.
Exactly. So there will be stuff that goes like some number, and it involves any coupling with a loop factor, but there will be all of them, okay? And indeed...
so sorry, but now I want to ask... Sorry,
go ahead.
Because normally the renormalization of these kinds of theories has the structure, right, that lower order operators only renormalize higher.
Yeah, this is still the case. In fact,
not renormalization, but somehow this is not respecting that kind of structure. The higher order stuff comes into the lower arcs.
Exactly. So
already at one loop, all of them come in.
Yeah. Well, what you're saying, is that, for instance, this B4 contributes to the running of G4, but it comes from G2. So they all go up.
Yeah, right.
Exactly. They all go up, but then they come all back.
You compute the arcs.
They go away and they come back, and they come back as you're pointing out in a striking way. Indeed, you have a lot of stuff here with all the couplings, and this is it small? Is it big? Well, the interesting thing is that up here we had that G4 is equal to G2 is equal to G6 in unit of the energy. Here they're all the same size. So in this point here, these higher terms will all be of the same order. And there is no way that, it's still one loop is fine, but it will have to involve all the possible effective field theory coefficients. So there is no calculability. This thing here is incalculable. But there is a nice fix to that, which is associated to the result that at tree level, the couplings are strictly monotonically decreasing. So in this figure here, now I'm replacing the axis with the actual couplings as a function of the energy, possibly, the running couplings, and so on. In this figure, if I limit myself to this part of the plot, G4 is smaller. Because of monotonicity, G6 is also smaller. In fact, I'm here. And you're guaranteed that all the other guys are also smaller. So basically, imposing, I'll be there in a second, imposing that one of your couplings is perturbative, it automatically gets rid of the whole series. So limited to this area, we can make statements which are rigorous, in the words of Zwiebern. Sorry. It's a comment to Brandon. It's a private joke. Some years ago, Zvi asked in a talk about these loops, is it rigorous? And yeah, I like it, stuck with me. Anyway, sorry.
Trying to relate what you are talking as a ambiguity, right? But if we will discuss an effective Lagrangian and coupling there, it's not the same, right? Because then loop I would be iteration of Lagrangian.
Yeah.
So can you relate, I'll say, because when say Marcus asked him about effective theory, then it's effective Lagrangian, not amplitude, right?
Sure.
And here it is amplitude. And the difference, what you iterate and not iterate, how it can influence.
Well, iterate, you mean the fact that...
The loop it is an iteration of previous Lagrangian.
Yeah, this is the loop. You see, is the previous Lagrangian or the previous amplitude at 3 level was G2, G4, right? And now you have G2 times G4, G4 times, yeah, you have all of them. But what I'm saying is here is that in the context of this bounce, there is a region where this iteration stops after a while, and you don't have to care about it anymore. And it's the region here where one of the coupling is small, then all of them will be small, and the iteration will be under control as an output of your positivity.
But in this sense, you can reshuffle the result in terms of Lagrangian as well, right? Not in terms of the amplitude, but in terms of effect.
Yeah, exactly. You can use it as a starting point to compute them. Okay. By the way, the level at which this negativity starts is related to the first running coupling. Because of the dimension analysis that Marcus alluded to, G4 here is the first running coupling, and then the next guy, G6, can be negative. You have the same thing in other theories. The first running, after that, your positivity rules fade to gray.
Okay. G2 run?
G2 doesn't run because there is nothing that, well, all right, you think with this guy? And yeah, now I'm in the theory of a goldstone to sorry, I put it to zero. Yeah. However, the effect of that running doesn't propagate because well, no, let me stop here. Okay, there's a different thing. Okay, good. So let me erase a little bit because I'm going to a slightly different topic, and I need 21 boards here.
Sorry, can I just ask, just to try to clarify the rigorous sense here. So if this was a phenomenological theory, this was snatched or something, and I was really, I would want to make predictions, under some assumptions, right, for say regions of allowed parameter space. In the end, I would or I would not. I could make such bounds. Do I have to make some kind of assumption about the whole series, something like a power counting rule, or do you claim you could make bounds with error estimates, in that sense rigorous, without knowing anything about the power counting, just knowing that this leading term is there?
I will go more for the latter, but with this, if you want, you don't have to input the fact that these coefficients have to be decreasing and so on.
Yeah.
First of all, this study tells you where you start. You start at pi0 scattering, so this is the
all
G2.
those betas, you have inequalities on them, but even when you sum them up, you can get, you make the most pessimistic assumptions about them, you still get a bound.
You still get a bound, yeah. And it's yeah, exactly.
Okay, thanks.
Cheers. Okay, so this brings me to the second part. I mean, not as in morning, afternoon, but kind of qualitatively different approach, which has to do with the fact that so far we took this forward limit case, which was simple, it was beautiful in many senses with this theorem. However, for instance, this coupling here, this G3STU, was invisible to us because it vanishes in the forward limit, so there's no information that we could get out of it. And by the way, this coupling is related to the Galilean theorem, which is itself the longitudinal component of massive spin 2 fields and massive gravity. So in that sense, understanding the physics or the constraint on this coupling has important implications for phenomenology. There's another aspect here, is that when we discussed unitarity, we used only the optical theorem, the fact that the imaginary part of the amplitude is bigger than 0, but there's much more there. In particular, when you expand your amplitude in partial waves, unitarity is not a simple statement about one coefficient in your partial wave expansion, but every coefficient in your partial wave expansion has a positive imaginary part. So somehow you have infinitely many inputs from unitarity. And these have not been apparent in what we did so far, right? We only used the sum of them being positive, okay? Good. So in the next part of the talk, I will enter this regime of t different from 0. And so I don't want to repeat the whole things, and I also cannot, but one question is this analyticity structure once you go away from the forward limit. Most of the important results, axiomatic results in this field, were derived in the presence of a mass gap. So the case of massless particles, they were most interested in because effective field theories are more useful when you have light particles. We're not really into this radar. But there is certain one result, which is the fact that at fixed negative real t, then the amplitude is analytic in S, in complex S, of course, without the real axis where we have these non-analyticities that we discussed before. And indeed, let's have a look at a couple of examples that we're familiar with to touch this thing. For instance, in phi cube theory, in the unnatural limit of a massless particle, with diagrams like this, these go clearly like 1 over t, but if you're strictly negative t, this is fine. And the associated box diagram has some structure which it has, many features, but in particular the type of things in 4 dimensions that we're looking at is things like log of s, log of t, of minus s minus t, and this thing is fine in for negative t. This is finite, and the amplitude is indeed analytic over there. This is an example in QFT. But it turns out that even in string theory, the Veneziano amplitude which you can write as where these alphas are these ray trajectories or function of S and T. So in here, you can famously write this as a sum of individual poles in the S channel or in the T channel. And if you do this, you get these residues. And the residues are, they encode the fact that this amplitude being fully crossing symmetric in STU, this amplitude has poles in the T channel. But the poles in the T channel appear for positive T, okay? So as long as we restrict ourselves to negative T, the Veneziano amplitude is also respecting this analyticity structure. And last but not least, you might have heard of these anomalous thresholds. These are examples where an example of this is a diagram of this type. In a theory, we have our usual particle with mass m that so far will be taken to 0, but I'll just write it here in generality. And then if you have another particle with mass big M, the diagram here turns out to have, of course, a branch cut, a pole. It starts at T equal 4 big M squared, corresponding to this cut here. But then there is another one, and this is physical, because it corresponds to the position where these two particles, they go on shell, okay? But then there's another one, which it's, when you compute this loop, happens at this value. And it happens only when m squared is, let me put it in, or m squared bigger than 2 big M squared, okay? So when the mass of the particle you're scattering is bigger than twice the mass of the people in there, you can have a singularity also arising from this thing. And the important thing, and the reason why these are called anomalous threshold, is that while here you can associate a unitarity, a physical process, to this thing you cannot really do, okay? Now, again, this thing happens for values of t which are bigger than 0, okay? So indeed...
Francesco,
yeah.
You get the branch cut at t equals 4 m squared is physical, and then what's the second one? Is it a branch point, or is it...
I think it's a branch point, but no, I'm tempted to say it's a pole, but yeah, I remember looking at the expression, I think it's a pole, but maybe it's a branch cut, right? No, it's true, these are the end, sorry, these are the end points of branch cuts. That's what this is, sorry, you're right. Yeah, no, it appears as a pole because it's integrated, sorry, it's a branch cut. Yeah, this is the starting point of the thing. It goes deeper into the...
And it's on the real axis?
It's on the real axis for positive, well, yeah. So, right, this was just to give you some taste of theories that you might be familiar with and what is their analytic structure. Now, there is in fact a further step here, a more, a stronger regime of analyticity, which is called maximal analyticity. And the idea is that the amplitudes that respect this hypothesis are analytic for complex S and complex T up to the unitarity implied discontinuities. Okay? So in these cases that we have seen, this anomalous threshold would not respect this property here. However, so this is, in general, you would think, okay, this is not a good assumption. But there is a context in which this is believed to be a good assumption, which is when you're scattering the lightest particle. Because you see here, this anomalous threshold originated only when the scattered particle was heavier than some other state in your theory. But if you are strictly asking that your scattered particle is the lightest, then you're not going to meet this anomalous threshold. This is not something that was proved with the same rigor as other statements in this business, but that it was not disproved either. So there is evidence that this is there, but for the lightest particle maximum anomalistic assumption. Yes?
Are the quantum numbers such that M can decay into 2 capital M?
M, you mean the small m?
Yeah. So it's actually an unstable particle.
When it's in this regime? No, sorry, that would be 4.
Oh, 4.
It's squared.
Oh, so it's still stable. Okay.
Yeah.
Thank you.
Cheers.
So it still could be in the S matrix.
Yeah.
No, that's a problem.
No, it's actually a beautiful thing, and it would be nice to if somebody were able to prove it already in a diagrammatic approach. And there's this nice story that there are some diagrams that are within other diagrams that are known to be non-analytic, but when inserted in a bigger diagram, they cancel out.
So it has to be less than 4m squared, or else it's not in the S matrix. Right?
Yeah.
But it could be that even this polynomial limitation in the theory does not work, right? I'm not sure.
Correct.
The theory
Indeed.
exists.
Yeah, no. As I said, there are no rigorous statement about this. It's more of an observation that so far works in all statements. And even the polynomial boundness that you are alluding to, yeah, this is also an assumption that is not proven. Nevertheless, it's a bit easier if I make this assumption in what follows. It's not, strictly speaking, necessary. I could have gone the other way, but it would have taken me a bit longer. So what I'm saying is that for the theories that I'm studying, whether we make this assumption or the other, eventually it doesn't matter. We get there a bit longer, but this is, well, hope faster. Okay? And good. So I'll do this assumption, and I'll introduce a tool that maybe many of you have not seen before, or some of you have. And you will ask why I introduce it. It's a bit complicated, but I think it's actually quite rewarding. Is crossing symmetric dispersion relations. Okay? So. This is something that was proposed many years back by Oberson and Curie in, what was it, 72? And I would say that now, the reason why it is interesting to look at it now is for completely different reasons, but I can tell you much more about this if you ask me. It's just a beautiful tool. Why? Because we said this morning that the amplitude is a function of S and T, in fact connects the 3 channels, right? The S and T and the U channels. But if you study the amplitude at fixed T, like we did at T equals 0, you have access only to 2 channels, S and the U channel, right? There is no information there about the T channel. And indeed, if you proceed with fixed T dispersion relation, as we will see later, eventually, to get information about this type of couplings, you need to put this information about the T channel. And this is a bit of a detour. Instead of crossing symmetric dispersion relation, what they do is that they automatically connect ST and U channels. And in this way, they have an object that knows about this full analyticity structure. Okay?
But analyticity immediately gives you channel if you continue to.
The U is fine, right? But the T.
So in this way, still, I'll say, in form of analytical attenuation, you would know what would be there.
No, it's there. It's just that to tell your dispersion relation that it's there is not so easy. Maybe it's a practical problem. I wouldn't know how to say. You definitely know that the thing has to be connecting the three of them, but the fact that you have developed a fixed T, then crossing symmetry is hidden, and to get it back is not so manifest.
The problem is that there's two complex variables. So you have to study the properties of two complex variables, which is much more powerful than the study of a function of one complex variable.
Right. I will stick to one complex variable. So you're right that now.
But that crossing symmetry requires two complex variables.
Exactly. So now we're exploiting this regime, two complex variables.
And those are totally different.
Totally different objects, very difficult to do.
Relative completion, there's all kinds of
Exactly.
effects of having two complex variables.
I'm not going to be that ambitious. I'm still going to take one slice of this space.
I think you need both to even do crossing symmetry.
You could. You could build double dispersion relations, both in S and T. On the other hand, there is since you have the full, I don't know how to draw it, you have the full four-dimensional T and S.
Dimensional space required for crossing symmetry.
Exactly, but here you can take a slice that keeps crossing symmetry manifest. This is a very special slice, and that's what I will get to. You're right. So we have S is complex, T is complex. I don't know how you draw this, but this is T and S, and it's a thing. And here, in here, the branch cuts that are implied by analyticity, and normally you could project for S complex a T fixed, right? That's what I was mentioning before, and we get the. I have a different color code now. We get the S and U. Okay. Now here I will do something else, and this is fixed T. Here I will keep a different variable fixed P, which is manifestly given in terms of a crossing symmetric expression. So that's why you're allowed to do this.
But when you're saying T is fixed, you're implying that T is fixed without, it's not a complex number, right? You're implying that T is
exactly.
in the range.
It's physical range, yeah.
It's physical range, right? But in principle, when you consider what was discussed, two variables, then T is generically is also complex.
It's also complex. Yeah, no, indeed, here it's complex. It will be complex, right? Yeah. It's under this extra assumption of
staying on the constraint that S plus T plus U is a constant.
Plus T plus U. Exactly. Of course, that's always the case. Yeah.
You don't have to, but you can.
Yeah. Good. So what is the structure here? Okay. I hope I'll be able to draw this. Okay. So there is a mapping which I will show here, but let me show what is it mapped to before I get to the details. Okay. This is infinity. Okay. And a whole box of charts here to get this right.
So you're fixing P squared, and this is what plane? What complex plane is this? This is the P squared.
It's this one. No, it's the one, where these are equal, but they are complex, right? So I wouldn't know how to spell it.
Easier to use triangular.
You mean the wedges, or no? STU. Yeah, in that plane, you mean I like to put the axis straight, but yeah, what I meant. You mean this? Yeah, this is for real S and T. Sorry, the one you meant is with this tilted, right? Indeed, this is a cross section of this thing. Let me show you.
The other thing, T was some negative number, and then
Yeah.
when you're plotting is S.
Exactly.
And this thing, P squared, is some fixed complex number.
Yeah. Yeah.
What is
What I'm plotting. Sorry, you want it? I would.
I just want to know what
It's taking me a bit longer to do this plot, so I'll show you the formulas, and then I'll devote it myself to the plot. So the map is to two different variables, Z and P, which they have this form. It's important that there's a rational function because it does not introduce branch cuts because of the change of variables, right? But the actual shape, I mean, we can talk about it, and is maybe not. It's more interesting to look at the actual.
It's important that P have square root singularities in terms of T.
It's important.
P itself
Yeah.
is the square root of that thing on the right-hand side.
Yeah.
So it's not an analytic function of X and U.
True. I will, since I'm going to be working with fixed p square, that's what I was saying, that we're taking a slice of this space, it's fixed. So it's not, we're not so interested in analyticity in P. In the,
And you just use, not take the square
yeah,
root.
I'd
exactly.
be happier if you
Fine. It was just
called
to-
a different name and call it Z.
P2. It's square because of the dimensions.
I know, but if you're going to think about the analytic properties in P without taking the square root.
I'll try to call it P. The likelihood I make a mistake is high, but maybe
It's not
not.
an analytic map, right?
Yeah. Fair enough. Since I'm working at fixed P, yeah, but you're right. Right. Sorry, I realized that maybe you guys don't see, but I'll write the U here. So this is just rotations by of this S by a number e to the I 4 pi Z and P. Okay, good. So it maps to this thing, and here, let me finish the coloring. Okay, and then there's another branch cut here. Okay, so this is the T. Oops. This is the T. This is the S, and this is the U channels. On the ring, we have S and T and U real. This is one maps to this plot here. Okay, and there are some other branch cuts with the same coloring along these three axes. Okay. Once you have this map, I mean, you just map these singularities here, and you discover it's here.
So
Yes.
the cut, like for the S channel cut, the physical side of the cut is the outside or the inside?
Here.
The S channel cut.
Yeah, but it's.
You're coming to the U channel cut.
Sorry.
The
Yeah.
physical side is
Good.
the outside or the
Yeah.
inside?
It goes from the outside and the inside. It's there are two parts.
Which one corresponds to the one that I usually would write above the x-axis? That's
Yeah, both. This it would be. Oops.
both. That's confusing.
Yeah, no, it's split in two pieces. It's not bad. Sorry,
Sorry, S
bleeding.
real plus I
Yeah,
X.
what's
Because-
the I epsilon prescription?
yeah, the I epsilon prescription is here and here, and
Jumps?
it jumps. Yeah, and the reason is that Sorry, now I messed up with these things, but it's more useful if you also see this guy here, right, as a discontinuity. Then you're like, yeah, that's why there is a discontinuity there. Yeah. So I understand that this is pretty messy, and I never listened to talks on crossing symmetric dispersion relation. I hated them, and I thought that's an extra thing. Why do we need it, and so on. Until I think pedagogically it's beautiful because it introduces this aspect of maintaining crossing symmetry, which is a beautiful and an important property that our amplitudes have. It is not manifest at fixed T. But then there are many beautiful features. You will see one in a moment, but I can tell you many more if you're interested in.
It's only
Yes?
relevant for the external particle.
It's irrelevant if they are identical.
It's only relevant.
Ah, yeah. Good, fair enough. Yeah. Otherwise. Okay, so what happens is that here they are real, but for instance, this is the S cut. Along the S cut, T changes. Let me write it here. T changes, and you can write it as a function of S as long as you're stuck to this gradient. And there's a complicated expression. I will write it, but I mean, of course, you don't need to pay attention to this. It's just here for the records. It's just to insist on this fact that, we're very different, in a very different regime with respect to fixed T dispersion relation. T evolves as you move along the discontinuity, okay? So you can already imagine where this is going in terms of the dispersion relations, right? There will be a T in the arguments that depends on S, so it will be a bit more complicated. Now, let me get to use this. So the analog of our logo picture is where we have the infrared, the UV. In this plot, it looks like, did I put the infinities? Yeah. Looks like this. There are these points here. This is the arc here. I make it purple. So the points here are where the ST and U go to infinity, okay? So the contour you start writing your dispersion relation on is really an integral over these poles here, okay? Then the UV is roughly that thing, and the IR is this the remaining thing once you deform it. Sorry, this is just the x-axis. The IR looks ugly, but I will argue that it doesn't matter. We are never going to integrate on the IR for some reasons that I can come back to in a second. Okay, so we have this beautiful logo, new logo, and the arc now will be done in this Z complex plane, and in particular, as I said, is the integral along this point. So along, if we call this point psi, which is just e to the I 2 pi over 3, so this is psi and psi squared, and so your amplitude now is an amplitude of Z and P squared. And in particular, we want to integrate it with the analog of the subtractions, right? The subtractions now are a bit different because we're not at infinity. The infinity comes from the 1 over z here. So softening the behavior there is made by a function that disappears in these points. And it disappears with the cube, so is the analog of the twice subtraction dispersion relation. There is a z to the 4 here that is there to ensure that in the infrared we get, when we do the integrals on the infrared, we get the quantities that look more similar to the stuff we were getting at t equals 0, okay? And then...
Just to ask, so make sure I'm not missing something really simple. So, I mean, this z-plane is some completely different plane.
Yes.
And so when you say these are the arcs, you just mean this is some contour that is closed, so the integral vanishes by Cauchy's theorem.
Exactly.
And I can identify UV and IR regions. And for some reason, too complicated for me to understand right now, this crazy thing is the simplest version of that, or is the most useful version of that, or something.
If you want, the starting point is that here, on these points, is the analog of the infinity contour.
So then you're trying to close the contour the rest of the way and identify UV and IR regions.
Not yet. Now I'm just writing the 0 here, what will give 0. And then I'll deform it into the blue and red lines and separate IR and UV like we did before.
Just doing little intervals around.
Exactly. Now it's just the little integrals on this thing.
Makes more sense.
Yeah. Is this, these 3 integrals here. Okay? And then, I mean, there's another piece of the function. It's not very important, but is there from dimension analysis and to actually, as I said, reproduce these things in the R. But the important thing is this that guarantees the Froissart, the fact that because of Froissart, this vanishes in those circles. Okay, now we can, as we say, we deform this into the blue contours and the red contours. And what we get is that, again, we get a relation between IR and UV. Now, the IR at 3 level when we insert the amplitude that we computed before, which is no longer here, but at 3 level it means that you don't have the non-analyticity. All the red here is disappearing, right? Okay, we never managed to use it properly. But what you left here is only the pole implied by this factor here, okay? So we might as well deform it in the infrared into that thing. I mentioned before that we're never going to compute in the AR, but even with loops, we're not going to compute in the AR. But whatever, it's just a side comment. But here it's very easy. It's really the residue here. So we put our amplitude that came from this, which was the one we had before. Now you put the z variables. I'll spare you the details, but what you get is G2 plus G3 p squared. That's it. You get only these 2 things, okay? Oops. Okay. And in the UV, instead, we get an expression that is an integral over z, the angle, etc., but it's useful to write it for you in terms of s, because it's something that we're more familiar with. In this, here s changes, so we can just change coordinates and write it in terms of s, and what we get is this, something that looks very much like the one we had before, from s bar to infinity, ds over pi, 1 over s cubed, and then you have 1 plus 3 halves p squared over s. And then you have the imaginary part of the amplitude as a function of s and t of s. T of s is how t changes along this arc. Okay. Good. Now, you notice that this thing now is no longer positive. This is not positive. Sorry? It's not positive.
I just said it could be.
It could be.
It's just not guaranteed.
It's not right, sorry. Not necessarily, right? All right. Yeah. It's not necessarily positive, but indeed, and here is the other thing that I mentioned before. We can expand this thing in partial waves and write it as sum of L, imaginary part of the coefficients of the partial wave expansion, well, let me call it L, of S, and then we have some Legendre polynomial of 1 minus 2t of S over S, okay? So we have something, it looks like this, and this thing is positive. So this thing is not necessarily positive because the Legendre polynomials oscillate. However, the Legendre polynomials are themselves always smaller than 1, right? Just bounded by 1. And they're bigger than minus 1. Moreover, if you are, in the case of scattering of same particles, here you only pick up the even guys. This expansion vanishes on the odd ones because of angles. This is just a small observation. There's even a 1/2 there. Okay, great. Good. This thing, the sum of these partial waves is equal to the imaginary part of the amplitude in the forward limit, because that's where all the Legendre go to 1, okay? This means that we can identify from this expression by considering that this thing is always smaller than 1 plus 3/2 p squared over s bar, the star of the integral. We can write the following thing, that the UV arcs as a function of p squared divided the UV arcs at 0 are smaller than 1 plus 3/2 p squared over s bar, and bigger than minus 1/2 1 plus 3/2 p squared over s bar. Nice. This is nice because you can make a plot of these arcs as a function of p 0 and a function of p squared. And this expression implies that it must be smaller than this line and bigger than this. So they must be in here. Okay. And on the other hand, the arcs in their infrared expression, they are given by this simple thing. It's just a parabola. And the parabola looks like this, G2 plus G3 p squared. Okay. There's one last ingredient, and then we're...
Positive G3. But you said that's
Sorry, the drawing is for positive G3. Yeah, you see where I would be going, exactly. There is yeah, exactly. This is G3 positive, and this is G3 negative, okay? There is a last thing that pops out from this analysis. Let me just drop it, we're all tired, and I'll just write it here, which is the fact that this p squared must be smaller than this s bar divided by 3. It's just the fraction that you took implies that this p squared must always be smaller than your scale, s bar and some units. Nothing special. But which means basically that our trumpet is really an end, and it's a value of 1/3. Okay? Good. Now, we can really do this analytically because we're just replacing this guy here. Sorry, mistake. It's divided by A0. What is A0? G2, good. Somebody was paying attention. It's a relief. Divided by G2. Okay. So what we get, you can play. I mean, it's so easy that I'm tempted to actually do it, but probably I will get it wrong. Anyway, is G3 over G2 in units of S bar, because the plot is actually there. It turns out that it's smaller than 3/2. Indeed, you see me, this is 3/2. So up here is also parabola. It's saturated by exactly these coefficients. And when you go down, basically saturated by that point there, and that's 21/4, which is 5.25. Okay? So this beautiful result comes like this from this crossing symmetric dispersion relation. There are many works in the literature that do this for fixed T dispersion relation, and then they use semi-definite programming with a lot of computational intensity. And I looked at the actual number they get is something like, if I get it correct, 5.18. Now, I don't know, maybe this is actually exact already. I will not get in the details, but it can be made better by some considerations. The fact that here we have a function that has only polynomials up to p squared. Instead, here on the right-hand side, we have a function that through T of S involves all powers of p. So there are some constraining, some constraints that you can put on the actual spectral density here that will give you a little bit of extra conditions. But I doubt that.
Yes,
It's yeah, exactly. It was implicit in the drawing. Exactly, minus. Okay, so yeah, this is the result of the second part, and is derived completely analytically. And basically, physically, what is this thing teaching us? It's telling us that even the couplings that we could not constrain with the moments and all these things that we discussed this morning, they do get constrained once you consider the dispersion relation between the forward limit. And in particular, they tell you that theories in which this coupling is much bigger than the one for pi zero scattering, right? Like the Galileans that would require a regime in which they're dominated by this coupling, that these theories are basically excluded by this bound over there. And in this class, this is mention of a work we did with Julia and Brando here in the audience. These Galileans happen to be the longitudinal polarization of massive gravitons of massive spin 2 fields. And basically, this type of analysis applied to this context tells you the following thing. I'll just take one more line and then we're done. So in roughly, in massive gravity, you have amplitudes that behave like, let me just call it spin 2. The context is actually different because we have amplitudes with helicity if you're actually looking at the spin 2, but I'll just give you a sketch of the parametrics here. So the amplitude goes roughly like this, and you recognize that here is where you would expect your G3, and here is where you expect your G2, right? And in particular, what you find from this expression is that G3 over G2 is equal the mass of the spin 2 guy squared. If we put it in that relation, we find that G3 over G2, which is smaller than roughly 5 times divided by S. And S, I remind you, is the theory cutoff. Or better, the effective field theory cutoff. So what we get by inserting this there is that the cutoff of the theory, S bar, must be smaller than roughly 5 times the mass of the graviton squared. Okay? So when you think about effective field theories, the picture you have in mind is that you have a particle with a certain mass that is parametrically smaller than the cutoff of your theory, right? Because this would give you a large separation scale in which your effective field theory is valid. But what we find here is that there is a fixed constraint between these two, and in fact, the validity of the effective field theory is really down to a very small regime. The actual number is not 5 when you do it, but roughly this is the story. Okay. The loops, which I will not talk about here, they are consistently improvable, usable, whatever, I don't find the word, but you can insert loops in this analysis, and with this crossing symmetric dispersion relation, you find roughly what we had this morning, well, an hour ago, sorry, that they still have a perturbative meaning in your dispersion relation. Contrary to instead finite fixed T dispersion relations, to do the same work, people take derivatives of the dispersion relation at T equals 0, where the loops explode. So there's a bit more difficulty there. But this framework is really solid to all of these things. And right, I think that's it. I'm happy to finish here.
Do these crossing symmetric dispersion relations, do they exist for fermions?
So in this form, no, because as it was noted before, you really need crossing in the 3 channels, and fermions they don't have this feature. Yeah. Yes.
The loops, like if I were to look at the IR part of the loops, does it show up in some finite way in this sum?
Yeah, exactly. So in this IR part, you will get. In this theory, right, you will have stuff that comes in with basically like similar to what we saw before, like G2 square, and then you'll have some logs of P, and I can't remember, it's P square, P to the 4. Yeah, they will look like this kind of things. And if you, but you see importantly that. The P to 0 limit exists because it's a Goldstone boson. This is what I was mentioning this morning. And therefore, you can make this plot where you divide by A0. And therefore, it's consistent. The loops are finite. And the question is how much the loop is here and here. Right here, we know it's roughly 0. But here, yeah. So contrary to instead fixed T dispersion relation, where these things would be infinity. Right.
Does this exist for the whole Goldstone boson? I mean, if you apply plus by plus scattering, that's also not crossing symmetric.
Yeah, there you can also use these things.
Somehow we use SU2 to relate one to
Exactly, and then correct.
So it really works for the whole multiplet.
Yeah, as a whole, it maps into different processes, but then it's
and the same sort of things hold
Yeah.
for this SU2.
exactly. Yeah. Sorry.
I was just wondering, like, in the spirit of exploring what your ideas and methodologies can do, have people tried that in maybe models that remain under perturbative control from the UV to VIR? Like, okay, like, so of course, like, the sexy thing in here is to connect something which has some degrees of freedom which are good in the UV with other degrees of freedom which are maybe good in VIR, okay, and try to make sense out of that by identifying constraints and stuff, okay? But maybe it's also, I don't know, maybe could be useful to actually do that in some settings, say Banks-Sachs type theories which remain perturbative in the UV but also in VIR, okay, but where still some non-perturbative
things.
Some non-trivial things are going on in the UV, okay, which are maybe, I mean, you know, Banks-Sachs is maybe it's still perturbative.
But I see what you mean, yeah.
People speculate about interesting non-perturbative physics in that conformal window, maybe kilotons and all sorts of things which may appear at low energies and need to be related where it comes. Is that something where people have looked into or where?
So I would say that because of this feature that I pointed out here, that at the boundary you tend to have weakly coupled theories, right? And this is true almost in all of these things. Also boundary that you obtain in this way, you eventually find that they are saturated by weakly coupled theories. So rather than going into models like the one you mentioned, where through this positivity type of approach, people have rather tried to study theories more stringy-like and to understand what happens. In particular, what was found is that certain, like this bound is saturated when you exchange a scalar, and instead this bound is much more complicated. There is nice work by Justin and Rietel Wang and company on this, and many other authors. But what you find is that the theories that saturate this bound here typically tend to have all towers of higher spin, so they look more like weakly coupled type of string theories. Plus, there is a new class of theories that pops in, which is it's not really a theory, but it's amplitudes that have certain that satisfy all the properties that we've been discussing here. This is an amplitude that satisfies crossing. It has the right UV behavior, this Frassard thing. So, but clearly it has poles on different channels, which is something that we cannot obtain within quantum field theory. Or a different way of seeing it is that if you focus on the S pole and expand this into partial ways, what you get is an infinite series of partial waves, m squared on the pole, right? So what does this mean is that when you look at the spectrum of this theory, that they really look like infinitely many resonances with all the spins at one value of the mass. And so if you want, the S-matrix approach has opened the door and some unwanted guests came in, and this is one of them. It's something that is not realized within quantum field theory. I'm not too worried about this because I think of this as the limiting case of stringy-like amplitude with a Regge trajectory and so on. But yeah, I would say that this is more the kind of things that people look at because of this weak coupling. The other groups I mentioned this morning, like Joao Penedones, Pedro Vieira, and many more that I'm unfortunately not spelling out now, they did more work on non-perturbative statements, and they did look at theories without finite coupling. But again, the implications for phenomenology are a bit harder to dig out.
Francesco, if I can ask you an open-ended one. So, prospects for going beyond 2 to 2. Higher point positivity is a Wild West, but like.
Yeah. What are the prospects?
Sorry, I didn't hear you. Going beyond 2 to 2. Sorry, higher point positivity.
Oh, beyond 2 to 2.
Yeah. So, I mean, there have been many directions that people have explored. Grant is not here, unfortunately. They had a nice work in trying with Nima in focusing on certain classes of theories in which you have a rigid extension to higher points, right? And there they could look at not really at positivity, but at certain ways of excluding those things. My feeling, but maybe it's naive, is that at least from this effective field theory positivity standpoint, is that when you open the door to higher points, you open the door to a plethora of other couplings. And I don't know, the naive part of me is that they will all be fixed. The amount of more couplings will be more than the constraints. But maybe not. It would be another surprise of these unitarity things.
In Grant's case, right, it actually was more constraining, right?
It was more constraining.
The space of the Stoke amplitudes is actually dramatically reduced once you hit the higher point. Now, of course, that's because there was a restricted class of
theories that extend. Yeah.
But so, okay, maybe if everything goes and you go to a higher point, then it doesn't, you don't get anything. But with some modest assumptions, it does seem to add additional power, and so you can hope that.
No, it would be nice. I don't have so many thoughts. Maybe other people have more. You?
It depends on what you assume about the higher point amplitudes. So if you make some assumptions about the higher point amplitudes and their relationship to the lower point amplitudes, you can get things out.
Like you might hope. I mean, what is my fantasy that you go from 5 there to 1.
All right, and that it will.
But I think that generically, I agree with Francesco that if you just allow anything, you say I have no more assumptions about the 5 point amplitudes.
There should be
it starts at 4m squared, so the gap is actually. Sorry, Ben.
There should be bound, because if we go back to the causality argument by building backgrounds, those exactly pick up backgrounds for many legs. You try to propagate, build a background that push you outside the line code, which is this is what making a sharp statement for the two, but.
Yes, sorry, you're right.
There's something similar logic to apply.
I mean, there's also just what we know from EFD paracounting, that I guess things with more fields in them should be suppressed by higher power.
Not in the heft.
Yes in the heft. Yes in the heft. Anyway.
But this is, saying you can get constraints on 5 points. I think saying you can get constraints on 5 point, like coefficients at 5 point, is different from saying that you bound the 4 point coefficient, like you get a smaller space at 4 point coefficient. Like, I think it is true that you would get constraints on 5 point coefficients. To me, the more interesting question is whether you actually bound the space any further and get something else.
Yeah.
Questions?
What if you try to go to a conformal theory?
To conformal theory.
It's a limit of massive theories, right?
Yeah.
Can you say anything, or does all hell destructive?
I guess there you can say much more without resorting to this type of things.
Well, I understand that, but I wonder whether this, as a then as a limit of this, do you get anything that?
But sorry, what is the? You mean some
parameter and I tune to a conformal fixed point.
What's the 2 to 2 amplitude? Conformal field theory. To what?
Yeah, what?
The non-conformal theory is continuously connected to the conformal field theory by going to the critical surface. So, is there anything you learned from this? No.
Not that I know of, but yeah, I'm not sure I know of. Well, there are people that look at the ADS-CFT and then
they do the reverse.
Exactly. It's more the
this historical nice example of the A-theorem that you learn about the flow from fixed point to another, exactly using this technique.
Yeah, so that the idea is that you couple.
What was your answer?
So you can learn about this monotonicity of the central charge from
Yes,
one
that's
point
right.
to another exactly using the dispersion argument.
Right, and also the,
Yeah. The thing that you do is that you couple your
right,
CFT.
also, if you look at radial
So, yeah,
quantization,
you're using it as a probe of the CFT. You're not
Yeah.
scattering an object inside the CFT.
if you look at radial quantization, then the eigenvalues of the Hamiltonian flow to the conformal dimensions. And that's a map, right? So it's not clear you should learn something, right?
Yeah, maybe. Yeah, no, maybe the
I mean, the
best example
Hamiltonian
is.
space S-matrix theory and Cross-up-bound and so on, right? And then there's a continuous flow from all the eigenvalues to the conformal dimensions.
Yeah.
If something crazy happens, there should be a relation.
No, I think yeah, if you are able to build it in a rigorous way, yeah, it's.
Okay, I think with that, let's thank Francesco.